All right, so remember that this week there's no class Wednesday or Friday. And the school, I think the whole school is closed Thursday and Friday. There's definitely no classes Thursday and Friday. Okay. And anybody have any homework questions or anything like that for statics?
I don't think you said anything.
Okay. So we've been just working on internal loads on inclined beams for a while. Now we're getting into the last topic in this class. It's the most different from the other topics of anything. You know, it's just kind of like a addendum to this class in a way. But the last topic is friction. And we're going to talk about three types of friction. The first one is square threaded screws. And second is belt friction. And then the third one is bearing friction. And bearing friction is going to be broken up into two parts. Journal bearings and thrust bearings. So the first one we're going to talk about is square threaded screws. And these are screws where the threads look like this. Bless you. Okay, so this is square threaded screws. These are harder to manufacture than regular screws. Regular screws look like this. And to manufacture threads like this, all you're doing is, well, it doesn't look exactly like that, the cross section, but you get the difference between the square threads and the non-square threads. For these, all you have to do is just cut out a little piece here. You just use a simple, what do you call that? Screw the tap. Yes. What? Yes. But the problem is with these, if you draw a free body diagram of, if you draw a free body diagram of the nut that connects to the just standard screws, you can imagine like the forces that are being applied are at an angle, those normal forces. And so if you think of a Newton's third law pair with the nut, the nut is receiving normal forces that tend to explode it, you know? And so the reason you do this is that this can support much bigger loads. So if you need a thread in a case where there's going to be big loads, you'd rather have it be a square threaded screw. So things like jacks on cars are square threaded screws because they're dealing with really big forces. Okay, these are easier to manufacture. But they're not good for high forces, for large forces. Okay, so before we get into the calculations of square threaded screws, I want to remind you of a simple thing from Physics 1 that's going to be the basis of this calculation, and it's not clear why it is yet, but so here's a Physics 1 reminder. Yeah, so blocks sliding along ramps. And so let's say this angle is theta, this mass is m. And remember that when you did calculations like this, just for simplicity, just to simplify the calculations, you used a coordinate system where the y-axis was pointing out of the ramp and the x-axis was along the ramp. You don't have to do that. You can do it in a standard coordinate system, but this simplifies more stuff than it complicates, so this was an easier way to do it. I want to point out that I know you didn't do it this way. You did it with you did the trigonometry, the cosines and the sines and whatever. But you can do this easily with a rotation matrix once you're used to punching rotation matrices into your calculator. So this is quick and easy with rotation matrices. So if you're going from a coordinate system like this to a coordinate system like this, then that angle is positive theta. With the ramp facing this way, it would be negative theta if the ramp was facing the other way. And then your rotation matrix is cosine of theta, sine of theta, negative sine of theta, cosine of theta. In the original coordinate system, the weight force is 0, negative mg. So in the new coordinate system, mg is equal to q times 0, negative mg. And that comes out to be negative mg sine of theta negative mg cosine of theta. You get the same answer, obviously. I think the way that you're probably used to doing it is you have this weight force like this, and you break it up into components like this. And then you just think about the trigonometry, think about the right triangle. But this is an application that, obviously what we're doing is just a coordinate system transformation, so you can always use that rotation matrix. We're doing this in a static case. So the way this would work is, well, let me put some other forces on here. So let's say that we have a force. Unfortunately, I'm also going to call this Q, but this is not a matrix. This is just a force Q. So Newton's second law says Q0 plus negative mg sine of theta, negative mg cosine of theta, plus 0n plus, we have to know which way the impending motion is going to be if this is a static case. If we're thinking of applying this force Q in order to overcome the static friction, then the static friction force is going to act down the ramp. And this is going to be the coefficient of friction times n. So this is negative coefficient times n, 0. And all this is equal to 0, 0. No acceleration. And so n is equal to mg cosine theta. Plug that into the x equation, and you get q minus mg sine theta minus mu times the quantity mg cosine theta is equal to 0. And so if you're trying to figure out the force Q that you have to apply in order to push this up the ramp, you'd get an answer of mg times sine of theta minus mg, no, I guess that's a plus in this case, mu times the cosine of theta. Okay, so that's the kind of calculation you did. So why would that be relevant for square threaded screws? Yeah.
It's just this ramp around this.
Yeah, right. So remember that. So yeah, what does this have to do with square threaded screws? Well, remember that for this simple drive friction calculation, the surface area of the contact between the two bodies never comes into it. Okay, remember, do you remember that being emphasized at all in Physics 1? Like, it seems weird, but like, if you're doing calculations involving friction, you were never given like the width of this, it doesn't come into the calculation. That seems strange, but that's how it is. So we can replace the idea of a square threaded screw traveling in like an external thread with a case where the entire thread of the screw is located at a single spot. This is not a good idea in practice, but mathematically this is what it is, you know? So that thing there is the entire thread of the screw. The external thread of the nut or whatever it is just an angled path like that. Okay, and so then from the side, all this is the sliding of a block up a ramp. Okay, yeah. Are you with me on that?
Why is I'm not understanding the shape in that
Okay.
first picture there. Why is it like?
It's supposed to be, that is just supposed to be the ramp just spiraling around the,
What's the skinny part between like
this and this?
I think it's the cross section.
Yeah, right. It's just the, I kind of just emphasized the ramp over on this side and not this side. But this is just, so this block is just sliding up that spiral.
So why is the block connected by like that skinny portion?
That's just to show that it's part of the screw. This is the thread of the screw, and the red is the thread of the nut.
Okay.
Are you with me on that? Well, there are a couple of things. So from the side, what you have is, if this screw has a weight pushing down, like the car, you know, the car on the jack, you have a weight pushing down like this. The thing that's making this slide up or down the ramp is, this isn't parallel to the surface. It's a horizontal force Q.
Because it has to be perpendicular to the weight.
Because the way you turn that thing is you have handles and you're just applying a couple,
yeah,
you know? Yeah. And the weight force points straight down. Where am I going with this? You have a weight force straight down like this. That's the W. So that's not just the weight of the thread, obviously. It's the weight of whatever you're supporting with this screw. Okay. So now, a couple of modifications of this. So we're used to doing this calculation where what's given is this angle theta, but like, you don't talk to a manufacturer and tell them what that angle is going to be. You tell them the pitch or the lead or whatever. So instead of being given the angle theta, you're given the pitch or the lead. Okay, so that's the first one. The meaning of these, so they often mean the same thing, pitch or lead. Lead is really the one that's useful to us. So let's think about these threads. And let's think about an ant climbing up this thread. Okay, so if you have a single thread, I chose an ant because it's easy to draw. If you have a single thread, then the ant, when he gets to this side of the screw again, is going to appear just one level above. Okay, so he's going to go this way. The next time you see him is going to be here. In that case, this is the lead. And this is the pitch. But there are also cases where you have a double-threaded screw. So this is single-threaded. When you have what's called a double-threaded screw, you would see the ant here. And the next time you see him, he would be up here. There are two independent threads going around that don't connect to each other. Okay, in that case, this is still called the pitch. But you can imagine for calculating the angle of that ramp, we don't care about that. We just care about how steep the ramp is on that ant is traveling on. Yeah?
Does a double thread help keep a screw more securely in place?
I don't remember what the purpose of a double-threaded screw is. I would guess that it has something to do with you could damage it and still, you could damage one thread and the thing could still be useful. That's my guess. But I don't know. But I do know this. This now is called the lead. Okay. So even though, all right, so look at that for a second and you understand what I'm saying here. Pitch is just the distance between two adjacent threads. But if those threads don't connect to each other, then that's not useful for our calculations. So for us, the lead is the useful measurement, because we're going to use that to calculate that angle theta.
I don't know if we're still doing like the inverse of sine or something.
What?
So we're just gonna do like the inverse of sine or something?
Yeah, right, that kind of stuff. Okay, so that's the first thing so instead of, if you look at this calculation for just the block on the incline, we have that angle theta. Well, that's not the way people talk about screws, so we're going to find a relationship between that theta and the lead. And then the second thing is that force Q. Like physically, can you imagine what that force Q would be? So these threads are, pretty small. Like if you think of like a car jack, the whole thing happens in that much space or something, right? That force Q is the force that you would use to turn this screw by applying, like, pushing your finger directly on the back of that block, like directly on the back of the end of the thread. Well, that would be a really inefficient way to do it. You'd have to apply a huge force. It makes a lot more sense to have like some kind of handle so you can turn it, you know. And so we want to relate that force Q to a couple that you apply to this. We're just going to think of it as applying a couple that turns it, okay? So the second thing is, instead of being given a force Q, we're going to be given a couple M. And the relationship between those is that M is equal to that force Q times the radius of the thread. And so if you want to know what this Q is, you can always re-express that as M over R. Okay. Well, I suppose let me I know you can't do this, but maybe I would say draw an arrow, and let me just put the relationship between the angle and the lead of a screw in here. Okay, so just draw an arrow from number 1 down, circle it, so you have it connected in your notes. But the relationship here is that if you're given the lead, and you want to know the angle of the ramp, this is the lead. What would be the horizontal in this? So if the lead is going exactly 1 time around that curved ramp, okay, then the horizontal is going to be the circumference. And so that's going to be equal to 2 pi r. And so theta is equal to the inverse tangent of L over 2 pi r. Okay, well, let's do a example problem. So let's say we have a single threaded square threaded screw with the radius of 0.01 meters. And a lead of Well, actually, let me change this to the pitch to just emphasize one thing. A pitch of 0.004 meters and a coefficient of static friction of 0.1. If the screw is supporting a weight of 2,000 newtons, first, what's the couple required to initiate motion up? And second, what's the couple required to initiate motion down? And those are going to be different magnitudes because the weight that's being supported by the screw is going to help move something down the ramp, and you're going to be fighting it to move it up. So it's always going to take a little more of a couple to get something moving up the, up the external thread than down the external thread. Okay. So why did I say this thing about single-threaded screws, about this being a single-threaded screw? It's because I gave you the pitch here, and if it'd be nice if everything just gave you the lead, but I'm just trying to emphasize the relationship between these two things. If you have a single-threaded screw, the pitch and the lead are the same. If you have a double-threaded screw, the lead is 2 times the pitch. Okay, so first, initiating motion up this ramp. So if we're trying to find this angle theta, 2 pi times 0.01 is the circumference. So that is 0.0628 about. The pitch is also the lead, and that's 0.004. And so that tells us that theta is equal to the inverse tangent of 0.004 over 0.0628. And you get a value for theta of about 3.64 degrees. And now we can think about this calculation. We have an angle of 3.64 degrees. And our block has a weight of 2,000 newtons. We're applying a horizontal force of Q. I'll relate that to M, to the couple, after we figure out this Q. There's a normal force. Well, I'll draw this stuff in a free body diagram, I guess. So free body diagram. We have a weight force of 2,000 newtons. An applied horizontal force Q. A normal force N. And if we're trying to initiate motion up this ramp, the friction force is down. And that's going to be equal to the coefficient times the normal. A rotation matrix for this is cosine of, well, let me draw the coordinate systems. So we're going from this coordinate system to this one. That's a counterclockwise rotation. And so theta is equal to positive 3.64.
Oh, small.
Yeah. And so the rotation matrix is cosine of 3.64, sine of 3.64, negative sine.
Also, now this will go on here with the human sense.
Yeah, right. Yeah, I mean, it's this. It serves the same purpose as the arrow over vectors. Okay, so what are we going to use this rotation matrix for? There are two forces that we're going to probably want to use this for. You could do both of them using just regular trigonometry, but that applied horizontal force Q and that weight force of 2,000 are both a lot easier to represent in a standard coordinate system. So we're just going to represent this as positive Q, 0, and this one is 0, negative 2,000, and then we're going to multiply those to the rotation matrix. Any questions about that? Like, what's the purpose of that? So Q times the force scalar Q, 0, is equal to 0.998 Q negative 0.063 Q. And Q times 0, negative 2,000 is equal to negative 126.98, negative 1995.97. And so now we can put this all into Newton's second law. We have negative 126.98, negative 1995.97, plus 0.998 Q, negative 0.063 Q, plus 0N, plus negative 0.1N, 0, is equal to 0, 0.
So can you do this the other way and use the rotation matrix on the other two forces?
Yeah, you could do that. Yep, that's right.
Okay.
Yeah, so then you'd have your rotation matrix, theta equals negative 3.64, and you'd be multiplying it to the normal force and the negative 0.1 N force. But don't do that. That's crazy. Okay.
Okay.
Okay. I never want to have to grade that. Okay, so you got two equations for two variables. The first one, you got 0.998 Q minus 0.1 N is equal to 126.98. The second one says negative 0.063 Q plus N is equal to positive 1995.97. You can solve that by substitution or reduce row echelon form.
Two equations, two variables.
What?
I just said two equations, two variables.
Yeah. Yeah, I mean, that's easy to solve by substitution. But I mean, you're so used to punching stuff in to reduce row echelon form, it might still be faster. I think that's what I do still. And what you get out of this is Q is equal to 329.31. N is equal to 2016.72. That's not quite the answer we're looking for. The answer we're looking for is the couple. So remember that the couple is equal to Q times R. And so that's 329.31 times the radius of 0.01. And so you get 3.29 Newton meters. Yeah.
Why is it so small?
Well, that's not really that small. I mean, you with a screwdriver, if you're cranking as hard as you can on a screwdriver, you can probably produce about 10 Newton meters. This has a big handle, so it makes it easier, but that for stuff that you're doing by hand, that's not really that small.
We've just been so used to working with huge forces.
Yeah, right.
It's like, it seems so small.
Yeah. Well, those couples are always small. I mean, for human-sized things, I mean, it's because that radius is so little, you know. But yeah, I think to me that's about right. If you think of how big a couple you can apply with a screwdriver, if you're just putting everything you have into it, it's somewhere on the order of magnitude of 10 Newton meters. So
Where does the Loctite come in?
Loctite, well, I guess you could think of that as, that's just probably, you could think of that as an external couple you have to overcome. I don't think it's exactly friction, you know. I don't really know how Loctite works, but I would think of it as just like you have to apply a certain couple just to bust the sort of seal on it or whatever.
I mean, it like fills the threads and then it hardens.
Yeah.
Yeah, but it's not exactly like a glue.
Yeah.
Like it really.
Also depends on the term.
Yeah. I don't know. Off the top of my head, I would say that would apply like kind of a barrier couple that you'd have to apply to get the stuff moving, and then you could use these equations, you know.
Okay.
Or it would, I mean, I guess it would add on to these equations. But once it's moving, I would think the Loctite thing goes away. But I would guess you would add it on right here. 3.29 Newton meters for the friction calculation plus 2 Newton meters for the Loctite or whatever. That's what I would guess.
Okay.
But I'm going to take that out of my video for legal purposes. Okay. Any other questions about that? Okay, well, what would be different? I mean, I guess we'll do this calculation next time, but what would be different for the case where now you got your new tires on the car and you want to lower it back down? You want to calculate the couple that you have to apply in order to start the screw moving down. The free body diagram would be different in two ways. Oh. Hold on a second. So now to start the screw, moving down, you still have the same angle, but now you're applying your force Q this way. The normal and the weight force are what they were before. But now since the impending motion is going to be down the ramp, this friction force is going to be up the ramp. Make sure I did that right. Yeah. Okay. So we'll do that calculation next time. There's not too much more to it. You might be thinking to yourself, instead of going through this whole calculation, couldn't I just leave the variables in there and derive a formula for moving up and a formula for moving down? And then those could be on your test and you could just apply the formulas. And that's true, but I just want you to remember how this approximation works. So I want you to go through sort of the steps.
So, with this with internal loads too.
Nope. Nope. This is it. What I'm giving you right now is what you'll have to do on a test.
Okay.
Okay, that's all.